Hello, in this video we're just going to go back to doing some review, a little bit of a change of the guard. Let's look at an example. You can some people call this Heaviside function or Heaviside's function, the Heaviside function, what some people call it. And some, I guess, books and all that, instructors call it the Heaviside function. I didn't make any of that up, so. Let h be a function from r to r such that h of x equals 1 if x is greater than or equal to 0, and h of x equals 0 if x is negative. Then the limit is x goes to 0 plus of h of x equals 1, which does equal h of 0. After all, coming in from the right, h of x equals 1. Even at 0 itself, h of 0 equals 1. So the right-hand limit exists, and we are continuous from the right. However, we're not continuous overall. We're discontinuous from the left because the left-hand limit would be 0. The limit x goes to 0 minus of h of x equals 0, which of course that does not equal h of 0 because h of 0 equals 1. So we're discontinuous from the left, and hence we're discontinuous overall, even though we are continuous from the right. Okay. And when I say discontinuous from the left, that means we're not continuous from the left. But now separately keep in mind, we are continuous from the right, but we're discontinuous from the left. All discontinuous from the left means is that we're not continuous from the left. That's all. Nothing less, nothing more. Okay. But anyway, so note that the Heaviside function is discontinuous at 0, but this function is continuous anywhere else. When I say it, I mean the Heaviside function. H is called as Heaviside's function or the Heaviside function. Some authors define, now some books or authors or teachers may define h of 0 to be 1/2. It just depends. Which is fine, but this function would still not be continuous from the right either. Which is fine, but yikes. Back that up. I shouldn't have inserted the word still. But this one, if we do this, if we define h of 0 to be 1/2, in a way things are even worse, because now we're not even continuous from the right, because h of x equals 1 for x strictly greater than 0. You know, even if we did define h of 0 to be 1/2, h of x would equal 1 to the immediate right of 0. So this limit would still equal 1, but now h of 0 would be in disharmony, and we'd be discontinuous from the right as well now. You remember earlier we were continuous from the right when we had this definition right here, but if we do this right here, we would be discontinuous from the right. So with this definition, we're continuous from the right. We are continuous from the right. With this definition of h of 0, on the other hand, we're discontinuous from the right. Okay, ew, you know, of course the right-hand limit wouldn't change, and neither would the left-hand limit, but anyway. So that's the so-called Heaviside function. And now this is another guy called the step function. Now my notation is a little strange. I think they don't use these bars. I think they... yeah, I guess I could use these bars. If this just bothers you, you can call it step of x or f of x or whatever. So let f be the function from r to r. This is going to be the step function such that f of n equals n itself for any integer n whatsoever, while f of x equals the most positive integer n that is still less than x if n is a non-integer. If that's a little fuzzy, here's an example. For example, f of 2, it's the biggest integer that is still less than x. So if x is 2.77, then f of x, which is f of 2.77, would equal 2, because 2 is the biggest integer that is still less than 2.77. Okay? But f of 3 would equal 3, because we already said f of n equals n. It's different if we're an integer, we just equal ourselves. Now, f of 3.01 would equal 3 because 3 is the biggest, it's the most positive integer, it's the biggest integer that is still less than 3.01. But f of 1.999 would equal 1. Not 2, just 1, because 1 is the biggest integer that is still less than, and I do mean in the greater than and less than sense, 1.999. Okay. However, f of 2.0001 would equal 2. I could stick in a lot of zeros and this would still be true. So 2.0001 would, because 2 is the biggest integer that is still smaller than this real number right here. F of 2 would equal 2. F of negative 7 would equal negative 7. That's by this f of n equals n. Now be careful with negatives. F of negative 7.0001 would equal negative 8, because negative 8 is the most positive integer that is still less than negative 7.0001. Remember, less than means the negative direction. So negative 8 would be the most positive integer, would be the greatest integer that is still less than negative 7.0001. Okay. We want to stay less than negative 7.0001. We can't say negative 7 here because negative 7 is not less than negative 7.0001. When I say greater than and less than, I really mean the classic greater than, less than. I don't mean absolute value magnitude here at all. I mean greater than and less than. And f of negative 6.999, now that would be neg 7. Now that would be neg 7 because neg 7 is less than neg 6.999 in the ordering of the real numbers. We're going by the ordering of the real numbers, if that helps you, okay? So this is the so-called step function. We denote f of x as this guy right here, bracketed x. That's not to be confused with closed interval. I'm not talking about a closed interval here, nor was I talking about it right here either, okay? This does not stand for closed interval at all, okay? So then we have the limit as x goes to c plus of step of x equals c itself. Because coming in from the right, as we get arbitrarily close to c from the right, c, well, actually for any real number c it's true. If c is an integer, well, the troublesome case anyway is when c is an integer. Let's assume that c is an integer first. If c is an integer, then as we come into c from the right, you know, if you're just a little bitty bit to the right of c, then the greatest integer that is still less than you are is c itself. Like if x is just a little bitty bit to the right of c, but not far at all, still greater than c, but not by much, then the greatest integer, then the most positive integer that is still less than x is c itself. Because we want the most positive integer that is less than this x in here, and that would be c, because we're just a little bit to the right of c, okay? Now that's if c is an integer. That's actually the hardest case. Now if c is not an integer, guys, we've got it made. Let's say that c is like pi or something. Then, well, then the limit, if we come in toward c from the right, then it's just going to be the step of c. If c is not an integer, it's easy because we're continuous. It would just be step of c. Okay, now step of c would not equal c itself if c is not an integer. A minute ago when c was an integer, this limit was equal to step c, which is equal to c itself if we assume that c is an integer. But if c is not an integer, you know, this limit right here will equal step c. Okay, this limit will equal this, which is step c. But step c in that case would not equal c itself, because c, we're assuming from the get-go, is not an integer in this case. So in the case where c is not an integer, this is still true, but you can't say that step c equals c itself if c is not an integer. Step c equals c itself only if c is an integer, okay? Because this function spits out integers in return, okay? If you're an integer, you know, if you're already an integer, you're just going to get yourself in return. If you're not an integer, well, what's going to get spat out is an integer. Like if you're 2.77, you're not an integer, but what comes out of that function is a 2, so it is an integer, okay? So integers are going to get spat out, Okay, so if c was 2.77, the limit as we come in is x goes to 2.77 from the right. It doesn't, it doesn't even matter. I could kill the plus sign right here. If x is not an integer, I can kill the plus sign and just let the limit x go to c, and this limit would still exist and it would equal step c, given that c is not an integer, okay? Now, if c is an integer, things get sticky. Well, but even if c is an integer, the right hand is still good. This is still good even if c is an integer. The right hand limit, the overall limit is in trouble if c is an integer though, but we'll get into that in a minute. Okay, we are thus always continuous from the right, even if we're an integer. The left hand is delicate though, it's different. If c equals an integer n, then the limit as x goes to c from the left of x, it won't equal step c, it's going to be step c minus 1. Because if we come in from the left, if we come in, f of 2.999 would equal 2, not 3. But f of 3 abruptly changes guard and equals 3. So that's discontinuous, for example. And in fact, notice that f of 2.999 does not equal 3, it equals 3 minus 1, which is 2. So the limit coming in from the left of x, if c is an integer, then the limit as x goes to c of step x, if x is zoning in on an integer c from the left, if it's going right, we're coming in to the left, we're going right, we're going towards c, it would equal step c minus 1 if c is an integer. So if c, let's just say that c equals 3, and we're coming into 3 from the left. No, excuse me, a minute ago, we're coming into 3 from the left. So this is from the left here. Minus right here, remember, it always means from the left. So let c be 3, and suppose we're coming into 3 from the left. So the limit x goes to 3 minus, coming into positive 3 from the left of x. X goes in here. X is a variable, remember? So you want the variable x in here. But we're coming in from the left. So x is in your mind, imagine x spatially moving toward 3 on the one-dimensional line. X goes through 2.999, it eventually reaches 2.9999999, and then it keeps going ever so delicately toward 3. We keep going toward 3 from the left, but no matter how close we get, as long as we don't touch 3 itself, f of 2.999999999 equals 2. That equals 2. However, when we do f of 3 itself, we get 3. So step of 3 is 3 itself. But we need 3 minus 1 to get 2, because to the immediate left vicinity of x equals 3, step of x equals 2 and not 3. Because we're arbitrarily close to 3, but we're not on 3. We don't equal 3 itself, but we get indefinitely close to 3. But no matter how close we get, step of x equals 2. For any to the immediate left of 3, step of x equals 2. So we need to do step 3 minus 1 to get 2. And again, if c is an integer, now c doesn't have to be 3, I just picked on 3. But step c for an integer equals c itself. And then c minus 1, which is n, our integer n. So remember we equated c with the integer n, so that's n minus 1 by equality. But of course, now that does not, step c minus 1 does not equal step c, right? Of course, step c, take away 1, does not equal step c itself by the nature of arithmetic. So we are not continuous from the left. Again, why? Because this limit right here does not equal step c itself. The guy on the very left right here does not equal this guy on the very right here. That was exactly what we would have wanted, though, to have continuity from the left, but we didn't get it. So we're not continuous from the left. AKA we're discontinuous. We're discontinuous from the left. Showing that, so hence we have shown that the left and right hand limits differ by 1, and hence we have ruled out the existence of the ordinary limit at x equals c, which in turn, which is all the more going to rule out continuity at x equals c. Okay, and again, truth be told, since we are not continuous, and in fact, guys, since we're not continuous from the left, we're not going to be ordinary continuous either. But oh well. If x is a non-integer, however, then everything is good. The left-hand limit and the right-hand limit agree. So the overall limit exists, and in fact, they equal f of c, which is step c. So we're altogether continuous at x equals c if, you know what, I made a boo-boo here. I need to say if c is a non-integer, not x. So sorry guys. So if c is a non-integer, like pi or 2.77, whatever, then the left and right hand limits agree. They equal f of c. Everything pretty that could happen does happen, and we're continuous. And actually a pretty nice way at that. So that's all for that. That was called the step function. Take a minute to pause the video and maybe think about it a second. Here's some examples. The limit as x goes to 2, if c equals an integer like 2, the limit as x goes to 2 from the left will equal 1, whereas the limit as x goes to 2 from the right will equal 2. Of course, we're discontinuous. In fact, we don't even, so the overall limit doesn't even exist. The ordinary limit as x goes to 2 will not exist because these one-sided limits don't agree. However, if c is, here c was 2 up here, but if c is like 2.3, which is not an integer, then the limit as x goes to 2.3 from the left will equal 2. The limit as x goes to 2.3 from the right will equal 2. And alpha of 2.3 is step 2.3, which equals 2. We're continuous. Everything pretty that could have happened, happened, which is good. So for 2.3, we're good to go. 2, however, is much more fussy because c was an integer. When c equals 2 or any integer, life is fussy for the step function. And it's a consequence of how we define the step function. That's why things work that way. Anyway, we're fixing to change the guard, so I'm going to stop this video here. We'll move on to the next video. Thank you.